we can now say on this seismic line, we can predict where our reservoir is going to be, and we can predict where our source rock is going to be, our hydrocarbon source rock. The reservoirs will be these little high amplitude shoreline sands, and they follow this pattern right there, just like that you're seeing. Overall transgression, so up to about this point, I can't draw straight. So, if I can do this straight. There's your condensed section. The top surface is the maximum flooding surface. Condensed sections, remember, have the organic, very high organic matter, so that's going to be your source rock. Now, condensed sections are also very laterally continuous, so that can be a seal too. Be a source rock and a seal for these reservoir sands. We're probably not going to find much sand up here in the high stand. Okay, if we were looking for sand, it was in the high stand, deltaic deposits, they'd probably be way back up towards the left somewhere. Now there's a little fault that goes through here, and that kind of messes things up a little bit, but still, you can see that nice downlap pattern onto that surface. Okay, so what you've been able to do now is you've been able to determine where your reservoir rock, where your source rock is, and where your seal rock is on that seismic line. So, very good. And you can pick out a drill site. We did that yesterday. Where would you want to drill? If it was me, and I had all the money, where I'd drill would be I'd drill a well that came down like this, so I hit all those transgressive sands. So I'd drill kind of like a slant well in that case. You're going to have good seal rock, particularly for these lower sands that are beneath the condensed section. Okay, so you've got a good seal, that's the condensed section, and it's also your hydrocarbon source rock. So you see how easy it is. Once you learn the patterns, like I keep saying, it's all just pattern recognition. And so the pattern you see on that seismic is this pattern here. Now what is this stuff over here? If I can draw this again. Draw kind of a wedge here. I'm going to try to. So your transgressive sands are right here. Your condensed section comes across. What's this stuff in here? Geologically, what is it? Mud, yeah, shelf mud. Seaward of the shoreline. Yeah, good. In the delta, often when you get the slope on the delta, that usually is where mud accumulates and you don't have much sand. And that's why I say up here, you probably wouldn't find very much sand. It's just probably prograding mud, the foresaid beds of the delta, like I talked about yesterday. All right, great. So now you can go down to Peru and tell them where to drill their well. Okay? I don't know if this has ever been drilled or not. This hadn't been drilled when I got that seismic line from them. I don't know if they ever drilled it or not. Okay, so I want to go back now to this idea of these different frequency of occurrence of cycles. Progradation, transgression, progradation, transgression, and so on. So, let's see, where are we? Yeah, I think I'll use this slide to illustrate that. All right, well, this is a little bit complicated, this slide. What it shows is how you get different scales of cyclicity and how you draw these, essentially. How do you draw these? Well, let's have a vertical axis. I'm going to go to a light yellow color here. Vertical axis is geological time. This is what they call a relative sea level curve. And it describes how sea level falls and rises. So you see in this curve, when the curve is moving to the left, that means sea level is rising. And when the curve moves to the right, that means sea level is falling. Okay, so let's look at this first. And what do I see? I see, I'm going to start right here, and I see a little rise in sea level, and then a drop in sea level, and then another rise in sea level, and then the start of another drop in sea level. Okay. So what you're looking at here is one sea level cycle, and what these lines represent is the higher frequency of sea level change, of cyclicity. So what you say is, okay, well, I've got a rising sea level, so this is transgressive, but there's actually there's a little kick in there in that time, which means you had a little bit of a drop in sea level. So that's shown by the dashed line here. And then you had another rise in sea level. Then you dropped sea level. You rose sea level, dropped it, rose, dropped, rose, dropped, rose, dropped, rose, dropped, rose, dropped. Okay? So you've got two cycles of sea level. And remember, this is important because this is how the reservoirs form. This is the level you want to be at when you're doing reservoir characterization. You've got, I'll go back to this diagram here, where you've got four reservoirs that are separated. If you were a seismic stratigrapher and you did this sort of interpretation, that you've got a transgression here, and you stopped there, didn't take the next step, your reservoir characterization would be incomplete. Because it's that next step, those little higher frequency fall, rise, that makes your reservoir. So when you're doing this sequence stratigraphy, that's the level you want to work at. And the coarser the scale that you work at, the less detail you have, but the poorer the reservoir characterization you're going to have too, or a more unrealistic reservoir characterization. Okay, so we go to this, and now what we're looking at is, we'll go to the next column here. So we're going to look in this little interval here. And the way that's drawn, it says you've even got a higher frequency of cyclicity that doesn't show up in this particular diagram, but it does in this one. So we go from here to there. Okay, and that's represented by this. So overall, you've got a rise in sea level or a transgression. Okay. But within that, you've got a higher frequency of cyclicity, a little rise, then a fall, a little rise, then a fall, a little rise, and then a fall to sea level. And we could go to the next scale if we wanted, but we won't do that. That kind of becomes impractical when you start trying to subdivide in too much detail. But that's the way one describes or builds what we call a relative sea level curve. Relative sea level curve. So I'll just, guess I will look at this one over here. And you see you've got a fall in sea level, a rise in sea level, and then a fall in sea level. And superimpose that, you've got another rise and a little fall, rise, little fall, rise, little fall. Each one of those rises is going to deposit a shale. Each one of the little falls will deposit like a shoreline sand, like the prograding shoreline sand in the last example. So what you see here, this sort of representation, is basically this. Right there again. So you've got different orders of cyclicity. Remember, prograding, transgressing, prograding, transgressing, prograding, transgressing, prograding. Overall, the system is transgressing, but in this case, you've got 4 little progradational events. Okay, well, having said that, let's go back to this picture here with our, there's one thing I didn't tell you, and what I've been talking about all this time is that your sea level curve is basically symmetrical, the way I've drawn it, okay? Well, if that's the case, then why do I have this, where I have, remember, the vertical axis is geological time. So why do I have, say, we'll look at this one, for example, right there. Why do I represent this by a long time interval? Well, no, let me do another thing here. Yes. Why do I show this as a long geologic time interval for transgression and only a small, kind of like a horizontal line here for the progradation or drop in sea level? And I'm showing you this, but what I've really been talking about all this time is this. So what's the difference here? Have I been lying to you again? I don't think so. What this is telling you, or apparently what this is telling you, is that you have a very small interval of time which you drop sea level, then a long interval of time where you raise sea level, and a short interval of time where you drop sea level. So something isn't right. That doesn't fit my sinusoidal curve, my symmetrical curve. And why you get this sort of drawing like this, it's not really telling you that the drops in sea level are very rapid. What it's telling you is, remember where you get this information from. Where do you get these sea level curves from? Ultimately, you get them from looking at the rocks, okay? You develop the sequence framework and you got the fossils and all that stuff. Remember that when you have the drop in sea level, you get erosion. Okay, when you get the rise in sea level, you get deposition up in shallow water. So what's basically happening is you raise sea level, then you drop sea level, and you erode away some of the rock record. Okay, so that record is eroded away. And so it gives you an apparent rapid rise in sea level, but that's not really the case. We call this, I want to bog you down with too many names, but we have a name for this. This is a coastal onlap chart. And let's see, we got lost here. Okay, that display that I just showed you is called a coastal onlap chart. So here's an area with rocks, Pennsylvanian age rocks, that depicts the changes in sea level. And that was done by looking at the rocks. Wherever you found an unconformity, what's the definition of an unconformity? It's a surface where you've had erosion, and so you've removed some of the rock record. So you don't see the record of the fall in sea level. Not there, gone. So one way you can display is with one of these coastal onlap charts. Now, I don't use them because it's too complicated, the way I've tried to explain it. Here, so what I use is the eustatic curves, which are symmetrical. And if you look very closely, each one of these is symmetrical. So you've got, let's see, to the left is a rise in sea level, to the right is a fall in sea level. So I can look at now two different scales of cyclicity that I found by looking at the rocks, by developing this, by looking and seeing where there were transgressive deposits and where there were unconformities, and then another transgression, then another unconformity, okay? And I converted that from this sort of coastal onlap to a symmetrical sea level curve. So essentially what you're doing, I'm going to go back again a bit. What you're doing, not a real easy way to explain this, I don't think. But what you're doing is you have a symmetrical sea level curve. So sea level is going down and up, but every time it goes down, it erodes the stuff that was deposited during the previous rise in sea level. And so that's why you don't see it in the rocks. what you get then is an unconformity representing this part of the curve. Is that understandable? Maybe, hopefully. This is the scale that controls your reservoir. Very hard, especially after lunch. Okay, so I'm going to take now, and again, the vertical axis is geological time, and I'm going to follow that curve, and I see what's happening. If rise is to the left and fall is to the right, what's happening is sea level is rising at that particular scale. This scale happens to be in many millions of years. So over a period of many millions of years, sea level is rising. But superimposed on that are these much more frequent falls and rises of cycles, and they're symmetrical. Fall at the same rate as the rise, more or less. And so all of these little things here are little symmetrical sea level cycles. Now they're drawn differently. I've been drawing them like this, but the sea level curves here are really being drawn like this. Same difference, it's just turned on its side. Well, just one more of these curves I'll show you, then we'll get off of this onto something a little more reasonable maybe. But in 2008, a guy by the name of Hack worked for Exxon, and he was another one of those guys that he was a very good biostratigrapher and a seismic stratigrapher. So Exxon hired him and locked him away, said, don't come out until you have a eustatic global sea level curve. Why is that important? Because remember what I said, if sea level is falling here, the coast of Bolivia, it's also falling in Southeast Asia or somewhere else. So if we can age date from one location, if we can age date those fall-rise cycles, we can then develop a curve for another area, and we can correlate, we know the ages. So it's a way of obtaining the ages of deposition and erosion that way. Very complicated stuff. And this is so complicated, I mean, you can't really read this, but again, you've got, whoops, there I go again. But you've got, here is your coastal on-lap chart. That one there. Coastal on-lap chart, and if you look really closely, you see those asymmetrical curves. Then over here is the sea level curve, and the each of these high frequency ones is symmetrical. Well, they kind of combined it, but basically they're more symmetrical. Oh, excuse me, no, I made a mistake there. What you're looking at here is coastal on-lap charts for the Paleozoic rocks and for Mesozoic and Cenozoic rocks. But the point is, look how detailed they are, all of these little cycles. And Hack was a guy who went around the world and did a lot of biostratigraphy work on cores and logs and seismic, and put together this curve. And the vertical axis is age. So there were enough places where he could identify the age of a particular horizon So if you went to another place and you developed a sea level curve by looking at the rocks, you could then age date that sea level curve. Getting heavy, this stuff. But it's important to know. Okay, so what I tried to demonstrate there is that you have multiple scales of fall-rise cycle. That's the bottom line. Now, we'll come back to that a little bit more when we get more into back to the reservoir, but now let me go a little bit easier here. And let's just take one cycle, one symmetrical cycle where we have a falling stage, a turnaround stage, and a rising stage of sea level. And what we're going to do, let's see. So far, I haven't talked much about absolute age. I've been talking about relative age, high stand to a low stand to a high stand over a interval of geologic time. But I haven't talked too much about the absolute ages of those fall-rise cycles. And that's what I want to get into now. I'm going to skip these little diagrams. They're just repetitive. Boy, let's see. Not what I want to do. Let me drop down here and see where I want to. Well, okay, back up to this diagram. This is one that I showed this morning, where I said that actually you have different curves, whether you have a big drop in sea level or a small drop in sea level. If all we've been talking about really is where you have small drops in sea level on the shelf and in fluvial systems. So in that case, there's a terminology that you can use to describe that. And let's see. So we're going to look at this green curve now, rather than the red one. Okay, we have when sea level starts to drop, we have our sequence boundary, but sea level isn't going to drop very far. So, so we're going to get depth, well, let's see. I'm getting all hung up here because somehow these got out of order. I'm going to skip way down here for a while. Oh, okay. Okay, I'm going to skip down, go to here. Here's where I wanted to be. And I want to talk about absolute time. To this point, like I said, I've been really talking about geologic time in the relative sense. Now I want to put some numbers on this. And like everything else, there's a terminology that one uses. And so what you see here is the terminology that is used for these fall-rise cycles, the frequency of occurrence of these fall-rise cycles. Well, geologists who study the whole Earth, big-scale geologists, have determined that there has been one sea level cycle that covered about 300 million years. Yeah, geologists think big. And then another cycle that was about 225 million years in duration. Okay, so 300 million years duration for one cycle, and the second cycle, 225 million years. Big scale features. How these form is because the ocean basins are continually contracting and expanding. Seafloor spreading and subduction and things like that, continental drift, things like that, give you different volumes of ocean water. And so over this time frame, we'll say 300 million years here, we've had one fall-rise cycle. And then the next 225 million years were the next fall-rise cycle that brings us up to the modern day. Well, as reservoir characterizers, we don't care about that because what we're talking about is huge basin scale sequences of rock that occur that are deposited over hundreds of millions of years, tens to hundreds of millions of years. So we don't care about that too much. That is called what we call a first order cycles, the order of hundreds of millions of years. The next cycle down is what we call the second order, and that generally has been worked out to represent a sea level cycle every 9 or 10 million years. So now we're going down from 300 million years to 9 to 10 million years for one of these cycles. What we call a third order cycle is where you had a fall and rise of sea level on the order of 1 to 2 million years. Fourth order cycle is where you had a fall and rise of sea level about 100,000 to 200,000 years, 0.1 to 0.2 million years. And fifth order cycle, about 10 to 20,000 years. Now, there are specific geological reasons why you get these cycles. For example, the first order cycle is, like I said, is when the volume of water in the ocean expands. When it does, you've got a transgression. When it contracts, the other way around. When it contracts, sea level rises. When it expands, sea level drops. And so that's the cause for the first order sequences, and even for the second order. When you get down to like the fifth order sequence, this is a sequence every 10 to 20,000 years where you get a lunar orbit. The moon and the sun change their orbital frequency in about 10 to 20,000 years. And so you get different gravitational attractions. So at one point, when the moon is close to the Earth, you pull the ocean water. So that's kind of an expression of increasing the volume. And when the moon is far from the Earth, so you don't get much of a gravitational effect, that has the opposite effect, and it expands the ocean. A common one is glaciers. We know, for example, that glaciers occurred in Earth on a frequency of about 10 to 9 to 10 million years duration. And so when you've got a period of glaciation, what does that mean? It means seawater has turned to ice, glaciers, okay? So you're reducing the amount of seawater during a period of glaciation. So what does that do to the ocean basin? It drops the sea level. During an interglacial period where the ice melts, the sea level rises again. So there's different causes of these fall-rise cycles at different frequencies. And that's why, in a sense, that they all kind of overlap, because you've got all these different processes overlapping. Now, in reservoir characterization, the scale I work at is this one, these two scales here, third and fourth order. I want to try and figure out what has happened over intervals of 1 to 2 million years, because that'll give me the overall depositional sequence. But then the parts of that sequence that occur more frequently and that give you the variability or the heterogeneities, those are the ones that are going to occur about 10 to 20, 100 to 200,000 years. Okay, so I kind of work in that scale. And I look for fossils, for example, that'll tell me, give me some ages so I know a fall-rise cycle is a fourth order or a third order or a second order, so on. So that's what I like to do, is I work in those orders there. And I look for fossils and other indicators that will tell me when I've got third order cycles and then superimpose on those fourth order cycles. Well, here's a picture to explain that, maybe a simpler picture, where we have a third order eustatic cycle, sea level cycle, and the horizontal scale is time in hundreds of thousands of years, and the vertical scale is distance of or amount of sea level rise and the amount of sea level fall. So here the sea level has risen 100 feet. Down here, sea level has fallen 100 feet. So we have this third order curve like that. So you've got one sea level cycle, we'll say from the high point here to the high point there is one cycle. Or if we want, we can say one cycle is from here to there. As long as it's in this case, third order, 1 to 2 million years. So this happens to be this scale here. Here's 1 million years from there to there. So we're somewhere in a 1 million to 2 million year range. Okay, now by a different process, we get these fourth order cycles, maybe glacial processes, something like that. And this is the curve, a higher frequency curve for those cycles. So rise, fall, rise, fall, rise, fall, rise, fall, rise, fall, rise, fall. Well, the two of those are occurring at the same interval of time, over 1 million years, and so there you're going to end up with what we would call a composite sea level curve that incorporates both of these scales of sea level change. So what do we end up with? Well, we end up, if we've got a third order rise here and a fourth order rise, we end up with a big rise in sea level. If we come around, let's come around to here, we get a big drop in third order sea level and a a drop over here, what's going to be the composite? It's going to be this one here, meaning you're going to get a big drop in sea level. Over 100 feet drop in sea level. If we come down to this point, say down here, where we've still got a third order drop and another fourth order drop, we're going to get a big drop in our total sea level. Let's use another, use another color. What happens when we get like a third order rise in sea level, like right about in here, that corresponds to a fourth order rise in sea level? Well, we're going to get a large rise in sea level, okay, because the two are going to be constructively interfering with each other. What happens if we have a third order rise and a fourth order fall? Well, we're going to get just a small drop in sea level. So my point is that that the degree or amount of fall and rise in sea level is a function of the superimposing these different scales of change in sea level. So let's just take a couple of examples of that. So we're going to start again with our curve, and we're going to let's just arbitrarily take this 400,000 years. Okay, at 400,000 years, you've got a third order drop and a fourth order drop. So you're going to constructively interfere, and you're going to get a very large drop in sea level. Well, what's going to be deposited during a very large drop in sea level? Well, you're going to have those submarine fans. You're going to expose the continental shelf, and you're going to erode the shelf and deposit those big submarine fans, because you're having a large drop in sea level, which means the shoreline is moving quite a way seaward. So you've got all that exposed shelf that you can erode. So when you get a composite curve like that, and if you know, well, when you get a composite curve like that, you know at that time interval, you're going to be depositing submarine fans. What happens when you have, let's go to another point where you have a third order fall and a fourth order rise, and they cancel each other out. Okay, so you're getting no change in sea level over an interval. So what's going to be deposited then? Well, the shales. Shales are kind of stable, you know, so during this time interval, you're going to deposit a shale. So now what we have is we're building up a stratigraphy here where we have a submarine fan and a shale. Well, let's keep going with this curve. And let's go down to a point here. Well, here you've got still a third order drop in sea level, and at that time you've got a fourth order drop. So once again, you're constructively interfering, and you're going to get a big drop in sea level. So what are you going to deposit then? You're going to deposit another submarine fan off the basin. So now we have another submarine fan deposit, SF. All right, let's keep going with this. So now we've gotten two submarine fans with a shale in between. Let's go to this point where we're starting a third order rise in sea level. And at the same time, at the fourth order, we've got a drop in sea level. So they almost cancel each other out. They don't quite cancel each other out. What you're getting is just the composite is just going to be like a small, very small drop in sea level, which means your shoreline is just going to move a little bit in the seaward direction, not go all the way out across the shelf. So what are you going to get there? Well, you're probably going to get another shale with maybe a little bit of sand on it. We'll call this shelf sand deposited there. We'll skip along here. Third order rise, fourth order fall. You get destructive interference. So you get another very small drop in shale. What, by the way, do you get here? That's when you're going to get your big transgressive shale and your high stand. That's your condensed section. That's your unconventional reservoir right there. Then we have this small drop, so we might get a little bit of sand there. And finally, I think the last one I've got is this one. So, third order drop, fourth order drop, we get a big drop in sea level. So what are we going to get deposited there? Nice big submarine fan again. We'll call this in here a giant condensed section. Okay, so what I've done in a very haphazard way, I'm not a good artist, but I've built a stratigraphy based on what I know about the sea level. Where do I get the information on the sea level? I get that from the fossils in the rock record. Okay, so I've been able to I've been able to predict what the stratigraphy is going to be by doing this, by knowing the sea level curve and by knowing the different scales of frequency of the cyclicity. Well, if you go home tonight and you have nothing better to do, you can do this in my book. It reminds me, I'm going to give you guys a copy of my book. I'll give it to Julio, free copy, electronic copy. At break time, I'll give it to you. I'll put it on your memory stick, and then you can distribute it if you want. Just don't tell the publisher. I'm not supposed to do that. So, but this is one of the pages in the book. So if you have nothing to do at night, what you can do, I put in this little exercise here, is that at these different times, what's your deposit going to be at the third order scale and at the fourth order scale and at the composite scale, just like I went through here. The only difference is what I've done here. You ought to do this and then we'll take a break. The only difference between here and what I just showed you is that now I've changed the scale here, and these are in millions of years now, the numbers. So 2 million years, 4 million, 6 million, 8 million, 10 million years. Okay? That's all I've done. So we just take one of these. Why don't you guys try this? Okay, see, it's just a simple matter of doing what I just did here to see what type of deposit you would have at the third order and at the fourth order. Excuse me, this was down the second order and the third order. Okay, why don't you guys try that? Okay, just how you do that 2 million years ago. Where is that on this curve? Right there, roughly. So at the third order, you're going to have a high stand of sea level. At the fourth order, you're having a high stand of sea level. So your composite is a very high stand of sea level. Okay, simple as that. Why don't you take a few minutes and then we'll break, and or take a break and then do it after breaks once you get your blood flowing again after all this stuff. And see if you can figure it out. If you can do this, then you've got it all mastered. You understand it all. And once again, these are the scales that I use when I'm doing reservoir characterization, because those are the scales that are important in giving you the stratigraphy that makes up your reservoir. So it may seem a little bit esoteric, but it is does have that significance. Okay? Anybody want to try that? Give up? The only way to learn it is to try it. So just draw a straight line at 2 million, 4 million, 6 million, 8 million, and 10 million years. And just fill in. You get a high stand or a low stand at the third and fourth order. This will be the third order. There's your fourth order. I'll try to draw this in a decent manner for you.
¿Cómo va el trabajo, Mafla?
Aquí estaba viendo los dos, aquí en dos, en el tercer orden.
Está subiendo.
Entonces, poner
Soy level rising, SL.
Okay, what I've done here is I've drawn for you
Mejor pon un...
those the times at which you figure out your high stand and so on. 2 million years, 4 million, 6 million, 8 million, and 10 million years.
No se pudo ir.
And remember, I
Salite de ahí
changed
igual
the
encima.
scale here.
Ponlo aquí. Ya, ahí ya.
To
Capa de color para el siguiente, en el cuarto orden, aquí,
Relative constant. Dale una raya para ver.
Yeah, I did change the scale on you, so now this is millions of years. So we also will.
Igual está subiendo. Entonces, right.
No puedes copiarlo ahí abajo. Van a estar copiando uno para. Ah, también. Puede ser cuando bajando.
Está bajando. En este otro cuesta.
Medio en este. No, bajando, porque mira la línea, estamos a un lado del plan. Está bajando.
Y este está.
¿Qué quiere?
Para que no me digas que no hay.
No te digo que no. No compartes. ¿Quieres llamar la atención? Como mujer.
Y aquí está bajando.
Agarrar los tres, borrarlos. Borrarlos. Este último borrarlo. Agarrar los tres. Los tres. ¿Por qué no seleccionan los tres?
No sé, mira, le pongo aquí.
No, con Shift. Shift. Ya, con. Lo estoy moviendo. ¿Qué?
Microsoft. Ya, en 6. Está bajando. En 8. Sería constante.
No le pongas constante.
Está subiendo, ¿no?
Sí, está subiendo.
Quiere dar la compra nomás. Pero está empezando a subir, mira. Pero es relativamente constante. No es constante. No sé.
¿Ves? No sabe.
Igual,
haz lo que piensas, después lo consigues cuando la persona muere.
A veces puedo estar muy
El otro es
equivocado
constante. Menos Jesus.
Y en este.
Eres perfecto.
Igual no, compuesto y es subida. Porque si aquí es compuesto y es subida, entonces es subida.
No, es constante.
Porque mira, está en la. No, pero a ver, se supone que tú estás construyendo compuestos. Ese es el ejercicio. No es mirar el compuesto. Eso es yo por eso. Si aquí tienes bajo y aquí tienes alto, ¿cómo se le compuesto?
No, pues depende de la magnitud.
Claro, depende de la magnitud, pero en general estaría subiendo, ¿no ves? Esto está compuesto y esto está arriba. Entonces,
No, pues, si está compuesto no sube. Aunque dependería del anterior.
del anterior. Pero, no sé,
Hasta
pongan
ver si
por lo
sube.
que crean y ahí vamos a ver.
What I've shown, put down here is another way that you can just express this, where you have
Está subiendo.
just call them either sea level rising, sea level falling, or sea level relatively constant. And you can put the fill in the blanks for that.
Abrazar a Julio. Para que no muera su energía, está bien. Sí, ¿qué quieres ver?